So, as was mentioned, I lead two teams at CERN that focus on cloud-native and machine learning platforms, and I also do quite a bit of work in the CNCF directly. But today, I will actually talk about something that is very close to my job and my heart, which is running scientific workloads on cloud-native infrastructures. I also have two children, and this is basically where this comes from, because we drive around quite a bit, and the question, are we there yet, keeps coming, so I thought it was a good topic for this. And the best use of Gen AI that I've found until now is actually to generate really nice cartoons for presentations. So just a quick introduction. I'm going to assume that everyone knows sort of what CERN does, but CERN is the European Laboratory for Particle Physics. We build large scientific experiments. Specifically, in this case, it's a particle accelerator that's called Large Hadron Collider, which is 100 meters underground when you accelerate beams of protons to very close to the speed of light and very high energies. And then we make them collide in very large infrastructures that are 100 meters underground as well. You can see the size of the person there to have an idea of the scale. These are basically acting as gigantic cameras taking pictures of what's happening in the collisions. Now, it's quite interesting because there's a very big computing challenge as well. When we do these collisions, we do around 40 million collisions a second. We generate a lot of data. We generate 1 petabyte of data a second. It's obviously not something we can store and analyze. So what we do is we do this filtering with different levels to reduce this amount of data. There's a lot of data we know we can just send away. Some of it we would like to keep more, but we can't because we are limited by the computing capacity. But to give you an example, this is the Atlas detector. In 1 year, it will be running all the filtering on one big Kubernetes cluster with 5,000 multi-core nodes and around 30,000 applications. My colleague, Giuseppe, that is responsible for this experiment setup, he gave a nice presentation back in Salt Lake City in November, where he explained what we are doing. So you have the 40 million pictures a second that generate 1 petabyte. Then we do some filtering based on hardware, custom electronics that we developed over the last 20 years. And this already reduces the data to something like 300 gigabytes a second. And then we have a large computing farm, which is this Kubernetes cluster that reduces from 300 gigabytes to something like 10 gigabytes a second that we can store and actually manage later. Now, the problem is that we have physicists that keep pushing us forward. So we are about to do an upgrade to the Large Hadron Collider that is called the High Luminosity LHC. Luminosity in particle physics only means more data. That's more visibility is just more data. And to have an idea of the scale, we are going to increase the data rates from where you see 300 gigabytes a second, we're going to go to 5 terabytes a second. And where you see 10 gigabytes a second that we need to store and analyze, you'll go into 50 gigabytes a second per experiment. So we need to do this. The main problem is generating more particles doesn't give us more money. It doesn't work like elsewhere in other businesses. We have a cap budget. So what we need is to be creative to do more with the same budget. And this is the main challenge we faced in computing at CERN. Now, over the last decades, we trusted something and relied on something that is called the Moore's Law, which is basically empirical evidence that the number of transistors was doubling every 2 years. And this gave us basically the evolution that matched the evolution of our needs. But the problem is that in the last few years, there's some evidence that things are flattening out, which means we need to look for new paradigms. So in the last, let's say, 10 years, we invested a lot in AI, especially deep learning, not necessarily Gen AI, to find new paradigms. And we started deploying GPUs and learning how to manage GPUs and all of these things. But it is a big change. And this is where we had experience with cloud native for services. And we started seeing, OK, there's a lot of investment in this area. Is this a solution? And this is the investment we've been doing in the last couple of years. Now, our use case is slightly different from running services, which was the original main goal of this. So we started looking at running cloud native also for scientific platforms. This will never stop. This is the other part I want to pass in the message, which is we see here LS3, which is where we do the upgrade that will increase this by 5 or 10 times. And then next decade, there will be an even bigger bump. So it doesn't matter what we are looking at today and having trouble. In 10 years, it will be exactly the same and as exciting as now. So I will give you a bit of a journey of how we've been handling this to get to running a scientific platform on Kubernetes. So here we see the beginning, which was what I call the early days, which is we were asking, can we run scientific computing platforms? And everyone say, I like CERN, but we don't really have this use case. And this is what was happening. But the first thing we had to do was, can we scale Kubernetes? So we started slowly. Can we scale Kubernetes to the scale we need? And Google had published this. We can do 1 million requests a second in a Kubernetes cluster back in 2016. So we said, OK, we want to be as Google. We want to do the same. We run it, and we manage. And we were all happy. But of course, we're never happy. So we did, can we do 2 million requests a second, which is what you see here. And you will see it started growing. And we did manage. But if you see, we were kind of cheating, because the latency there is like half a second, which means we were actually not making it. We actually had a huge downtime in the data center. Thanks to this, we became really popular in the department for the bad reasons. We caused a few outages, a lot of excitement. We burned an actual physical switch thanks to this effort. So it was quite spectacular. And everyone remembers it, even if it was many years ago. We did quite a few of those in this journey, which is also entertaining. So then we started saying, OK, we can scale single workloads to requests a second, 1 million. And then we tried looking, can we actually have a distributed infrastructure? CERN traditionally has what we call the grid, the Large Hadron Computing, World Large Hadron Computing Grid, which is 200 sites distributed around the world that kind of expose something similar to what Kubernetes offers, like interfaces for compute, storage, network, all of this. Can we do the same with Kubernetes? So we actually had an intern coming to during summer, and we tried to do this. On the top left, you see the distribution. So we have CERN and then a bunch of sites that are connected to us. Our goal is to run an infrastructure with 200 distributed sites that offer us close to 1 million cores back in 2016, running 500,000 jobs a day. And we could do this. But we also need more. We need what's on the other side, which says we need matchmaking of jobs. Jobs linked to jobs, jobs linked to nodes. We need fair share. We need the capability of doing preemption, other advanced scheduling primitives that were not there in Kubernetes because no one had asked for it. And the notion of a job in Kubernetes was just sort of a map-reduced job. It wasn't what we traditionally call an HPC workload and MPI and all these things. And we are also running htconda, which is a very similar tool to Slurm, to do this scheduling. So our first goal was, can we do this? And we did it, but we were actually only using Kubernetes to manage htconda. We were not scheduling the jobs using Kubernetes, which was the ultimate goal. But it was kind of an intermediate step. Fun fact, the person that worked on this project, Clenimar, it was his first talk ever. And he gave a keynote at KubeCon, so this was quite spectacular. I told him that he has to go upwards. He cannot go below this. So that's his threshold. What we also learned is that there was a huge community that was available to help us. And this is the key thing I would like to pass, is that it's the community that has made the success of all this effort. And we had other needs. We had one around container distribution. And I always ask this, so I will ask you, handling images when you have thousands of nodes, thousands of jobs is actually a challenge on itself because not all images are well structured. So if you had to deal with an image that is 10 megabytes or bigger, raise your hand. 10 megabytes. Pretty easy? Yeah? 100 megabytes? Raise your hand. OK? 1 gigabyte? Still lots of hands. 10 gigabytes? One hand. 100 gigabytes? No more hands. Otherwise, I have questions after if you have to deal with this. But we do, because people have ways of building their software that they cannot just easily change and adapt. And we could tell them, you should layer them like this. They will be optimal. And they would say, yeah, then I don't use it. It's too complicated. I cannot change my Fortran code from the 70s to be able to build things in that way. And they are right. Like, if we want to offer them a new infrastructure, we can't ask them to spend a lot of time redoing all the ways of working they have. So we learned that the community could help us, and we organized this workshop at CERN in 2019. And these people came to help us, like Bob and Jeffy, for example, that are now in the CNCF. Akihiro and Kohei from NTT Japan, which are like superstars. Phil from IBM. A bunch of people came. And this was in May 2019. By April 2020, we had Kohei publishing something called the STAR-GZ snapshot and announcing it, which is what we call lazy pulling, which means you remotely mount the image, but you immediately start your job, and then you just pull the files that you actually need for the job. Meaning we could have 100 gigabyte images. We even have 700 gigabyte images, and it doesn't matter. It just works. It's transparent to the user. And this is what we wanted. And again, this was something we saw first. No one else was looking into it necessarily, at least that we knew of. But these requirements came. And Google announced GKE image streaming just a year later. So all these things kind of are built by the community, which is one thing I really would like to stress. So we talked about the initials, then we didn't stop. Like, we kept asking, can we do it? And then we were talking about scale and distribution. So actually, we gave another keynote about this, which we had a very humble goal, which was to rediscover a Nobel Prize-winning experiment, redo a Nobel Prize-winning experiment live on stage at KubeCon. So as you do, what happened is that in 2012, there was an analysis of some data at CERN, which gave the discovery of the Higgs boson that gave birth to the Nobel Prize for Peter Higgs in 2013. We wanted to demonstrate that using containerization, we could wrap the workload in a container with software that was used in 2012, but actually with code from a lot earlier, including a lot of C++, but also a lot of Fortran. And we could take it and reproduce this experiment in a more modern infrastructure in 2019. And in the meantime, get a big improvement in the efficiency. So we did this, and we took a data set that was 70 terabytes. The original analysis had taken, with this setup, would take around 24 hours. And we took it, and we did it on premises in a Kubernetes environment with these components, the components that we are all used to. And we could do it in around 8 hours because we didn't get enough resources to actually do this in less, but we knew we could scale out. So we had a collaboration with Google that gave us access to 30,000 CPU cores, and we could do this in less than 5 minutes. And you can see the amazing data rates, and this was like a big success. But we also learned another thing, which is not only it's allowing us to be more efficient, but it also democratizes access to these kind of workloads. Like if you are doing science, if you don't have access to an HPC supercomputer or your own on-premises data center, it's very hard to do this kind of scale, very large scale efforts. With this, we opened up the possibility with a credit card for anyone that has access to the data set and the required knowledge to run the exact same experience with a couple $100s, which is also something that came out of it. So in the end, we show this plot that is all that physicists like is looking at plots. In here, you see especially the red growing thing, which is the expected discovery, what would be the Higgs. And then the black dots are the actually data from the detectors. And you can see the black dots match the red parts, which claims the discovery. So very interesting. Now, again, this was kind of a stunt because we were doing it in one cluster and using not many different jobs, just dedicated to one purpose. But as I mentioned, we needed these advanced scheduling primitives that were still missing. Now, we were making some progress, but not huge progress because the interest was still not there in the whole community. But there was something coming up. Like you see the scientists, we're saying, are we there yet? What do we need? But there was something coming from the back, like, which is symbolized in this small robot. And the things we needed and we knew we had already was we could do high throughput, we could do software distribution efficiently. We were not completely sure we could do the hybrid deployments, crossing boundaries between data centers, so the multi-cluster hybrid deployment. We were not sure about efficient NUMA awareness, and we didn't have the primitives for advanced scheduling, things like gang scheduling, quotas, queues, preemption, all the things that you need in a modern scientific computing platform. So in this case, we did a demo with a tool that was just appearing in 2022 called Q, which is an advanced scheduler for Kubernetes that is integrated into SIG scheduling that offers this kind of capabilities. So we did a demo where we had the 4 experiments at CERN, Atlas CMS, ALICE, and LHCb, represented, submitting their jobs. And from an admin side, we had what's called cluster queues, and we could move the workloads around. We could have different clients stealing from queues that are not necessarily theirs to kind of bump the overall efficiency, which is, again, something we absolutely need to do. And we could have a mix of on-premises clusters and public cloud clusters. So in this case, we use the Google Cloud as well. So this was the initial start of this kind of product. But then I would claim that right now we are there. And the reason we are there is not, it was kind of unexpected. And we were not sure we would ever get there. But then Gen AI came. And actually the biggest benefit for science from Gen AI has been that it has exactly the same requirements that we have in terms of advanced scheduling primitives, efficiency of using GPUs, and of the resources themselves. So they actually came up with a huge momentum and made these tools work. So just last November, we gave this presentation also at KubeCon together with Google, where we showed a real AI workload, deep learning, not Gen AI, no LLMs, just traditional deep learning, particle tracking, where it's basically the example I gave you of when the collisions happen and doing this picture and tracking where the particles are going in the collisions. We do this with a trained neural network, and then we do the inference live. And we did this demo where we were actually submitting the jobs to multiple clusters, some on premises, some on the public cloud, using tools like Q and Kubeflow to orchestrate it. And eventually, you could have something like Slurm also doing the same. So we knew that now we have the batch primitives we need. What we didn't know yet in November is, can we actually share this efficiently with interactive workloads? Because again, this is the other problem we have, which is if you have a very efficient batch farm, but you have this very less efficient interactive workloads where people ask for GPUs but actually don't use them efficiently, we need more. And this is a quick demo I'll do now of a new system where I'm claiming that this is our scientific computing platform based on Kubernetes. And this is what I will try to demo today. So this is an actual production cluster at CERN. The way it works is there's this level of shared resources. This is just Kubernetes clusters underneath with Q in front. And on top of it, we deploy all workloads we need at CERN. So this includes things like continuous integration with GitLab or GitHub Actions. It includes MPI. It includes AI, like training and serving, and we use Kubeflow for that. And it includes interactive workloads. And this is what's interesting here. For interactive workloads, we offer notebooks, we offer VS Code, and we offer something which is the #1 request of physicists for any platform like this, which is SSH access. So we can actually SSH to pods. So I'll do a quick demo now, if I manage to put this. OK. Hopefully this works. So not this. I will show you this. So in here, we are seeing a live cluster at CERN. It's a new cluster, so the efficiency is still not very high, but you can see all the sessions running on GPUs here, and you can see the live monitoring. So what I will do is I will just go to my personal namespace, where I have deployed a few workloads here. And you can see I have one session running. I'm very efficient, of course. You can see here my efficiency is amazing. I'll show you what is running there. So this is my own namespace. I will actually have to log in, so this will be interesting. Should have done this before. So just to show you that this is live. This wasn't planned, but we do two-factor, of course. This is just to really show that this is live. And hopefully this will work. All right. So you can see here, I'm working on a live cluster at CERN. This wasn't planned, but it shows even more. You can see what these workloads look like. All that physicists need to do is define this YAML. This is as much YAML as they want to see, where they say which image they want to use and how many resources they need and the type of resource. So I'm running one there, but I will just deploy one here. And in a couple of seconds, we should see something coming. And of course, this will work, I'm sure. If you've seen my live demos, usually there's some struggles, but There you go. So now I can exec to this pod and get a shell. This is what we will all do and are used to do. So I can show you here that I have my home directory. I have my user ID. This is very important. So you saw this rootless thing. I'm actually my own user running in the container, my CERN user. And I can also do things like who am I? And of course, I can show you that this is running with 2 GPUs, full GPUs. Now, what I told you as well is that in addition to that, I can SSH to the session. And all I need to do is give the name of my pod when I SSH. And you will see that there's a new bash process starting here. And again, as a physicist, I don't even know I'm running on a container, on Kubernetes, whatever cluster, doesn't matter, just there. The other thing I wanted to show you is that I can also get half GPUs. So I'll quickly create a new session here just to show you this, because I'm running out of time. But I'll just wait a little bit of time here for this one to pop up as well. OK. So it is there. I'll SSH to it. So it's pretty fast. And I'll just wrap it up. And in this session, so if we log, you will see that I only have 1 GPU, but not only that, I'm using what's called MIG, which is an NVIDIA way of partitioning GPUs, and I only have half of the memory, which is basically what I said here. I said I wanted 47 gigabytes of the GPU instead of the full 96. And just a last demo, the other thing that is also interesting is that in the exact same platform, as a user, I can see in my VS Code here my sessions, and I can also just attach my VS Code there. And again, this is all in the same cluster where I'm running the training, the serving, the interactive sessions. I can also get VS Code, SSH, the whole thing. And this takes a couple of seconds, but you can see here that it's already launching all these node processes that basically are required to attach a node session. So if I go here very quickly, before I'm kicked out, I am being kicked out. So I'll skip this part, but you can see the node is all here. So I'll skip this and go back to my presentation. This is the last slide. So again, I always thank the community. This couldn't be possible. We're all helping science to move forward. So thank you very much. And if you have any questions, I'll be around the whole day. Thank you.